Well, hi, hello, welcome to section 6. Thank you all for being here. So starting off with some announcements. I sent out the mid-semester feedback for like lecture section. Sorry that it was not sent out at the same time as the lab one, but Emma was wanting to send that out the day after y'all had your exam, and so I was like, let's let it mellow for a few days. Let's give them their scores, and then they can evaluate like exam one and how things like matched up with it. So that's why we're doing the evaluations for like lecture section separate from lab. We do read them pretty thoroughly. Like changes that are suggested in there have been incorporated in previous years. Like the reason we have practice exam explanation videos is because people were like, that would be helpful. And like if enough people are like, hey, actually we need more than 2 practice exams, then we will probably do something like that. Like it's also helpful for section because I always do a balance of like content review and practice. And some people are like, the time we spend in section, the solo practice is not helpful because like it's better to like have instruction time and like to be guided through it. Some people are like, actually I want more solo time to like finish the problem before we fully start talking about it, which like I'm sure. Some people are like, I like how section lets us get the basics down before tackling the hard problems. And other people are like, I wish we were doing the hard problems in section. So it's kind of like a lot of like balancing what everyone's preferences are. But like I will kind of do an aggregate of like how people are feeling about things after getting the feedback. And if more people are like, let's do more of like the harder practice and the easier stuff, then we will do that. Like, and if more people want to do more like solo practice versus more like guided practice where I'm kind of leading things. Another thing that I've done in the past with some questions that I really like is getting students to be in the hot seat of like getting them to start talking through some of the logic, and I workshop it with them. And it's kind of like a live tutorial moment. So, like, lots of things to try. We are going to be working some harder problems as we get further into it, like, especially, like, I know we're going to do some syntheses together in section 7 and 8, I think. But another thing to put on your radar is next week I'm holding my mid-semester meetings. You'll get more information about this as it gets closer, but essentially I set off 13 hours, I think, to meet with students, and I would love to meet with everyone in the class. I'm doing like 10-minute meeting slots, which is very like, ooh, like here we are. So for the 10-minute meetings, it's kind of like have a goal in mind. What is the big thing that you want to talk about or touch base about? Typically, it's about some kind of study method of what's working, or it's about something to do with like exam preparation. But it could also, like, if you're doing fine, like, it could just be like, how's life? Like, we could just chat. So it truly is like yours to do what you want with, but I do like touching base with everyone kind of one-on-one. Then with that, I am going to send out the signups for those meetings staggered. So the students who scored lower on the first exam, I want them to have kind of first dibs for availability just to make sure that we meet. And then I'm having them maybe sign up for 20 minutes instead of 10 minutes. And then like the next batch will be the next like 30 points and the next 30 points. And so between Friday and Sunday, these will be sent out to you. And there'll be an email that explains it, and there's a Calendly link. Yeah, I'm trying to think of other things. Are there any like logistical questions on y'all's end or things that y'all are thinking of?
Next exam is the 31st.
2 weeks from tomorrow. Yeah, so sorry. Yeah, no rest.
And the final's a week after.
Yeah. The chaos never stops, but neither do we. Cool. So a little bit about section 6, or lecture 6, like the content here. So it is reactions, but it's kind of a different game. Like all of the reactions for this lecture are pretty easy. They're like 1 or 2 steps compared to something like the acetal reaction where we were doing 6 steps, proton transfer, all the thing. Mechanism is not what's hard about lecture 6. What's hard about lecture 6 is when you have these 4 options of SN2, E2, SN1, E1, oftentimes it's the same functional groups that can do all 4 of these different types of reactions. So our skill and our main goal with the lecture 6 content is making y'all proficient at predicting which one of those reactions is the primary one that happens. So the way that the section of today is going to work is we are going to do kind of a like pit stop touch base with each of these reaction types, the SN2, E2, and we group SN1, E1 together. And then that's going to be the first about hour. And then for the last like 30 minutes or so, we're going to do some practice with that GFP system. The other thing I will say about GFP system is at this point I've seen maybe how like 15 different schools and I would say maybe 10 organic chemistry textbooks teach these reactions. The GFP method is the method I dislike the least. So like I don't think any of them teach it super well, and it's really kind of complicated because there are a lot of scenarios. In most organic chemistry classes, these are some of the first reactions that students are taught, and I think that it's like chaos. Like I'm much rather y'all in this summer class having seen like carbonyl chemistry and like amines, enamines, CAD stuff, because then you know kind of beats for mechanisms. Imagine learning mechanisms for the first time, reactions for the first time, having stereochemistry, and having to decide which one. Like that's a lot going on. The GFP system, though, I think does a fun thing of kind of gamifying this algorithmic thinking of how to figure out what's going on. And it's not perfect, but it is one of the better methods that I have seen. And so, like, the first time I saw this in 2019, I was like, okay, you kind of did that. Let's see. But without further ado, we'll get into section. I will say I'm busting back out the transition music to help kind of ease it because we're going to have a lot of hard pivots. So get ready for the first transition of the day. So let's talk about SN2. So substitution reactions, big idea is they substitute a leaving group for some nucleophile, or typically a nucleophile, but some other chemical group. The mechanism for SN2 is a really easy one-step mechanism. We call it a backside attack, where the lone pair on the nucleophile goes and attacks the sigma star between a carbon and a leaving group, and then we kick off the leaving group. We call it SN2 because, one, it's a substitution. We went from having a leaving group there to substitute a nucleophile. It's nucleophilic in that it's driven by this nucleophilic attack, and then it's the 2 because of kinetics. So do you remember Gen Chem? You talked about rate laws, and you had 0 order, first order, second order. You had integrated rate laws. Oh my gosh, so fun and fancy. We're not going to get into all that. But the 2 here comes from the fact that the rate of this reaction depends on the concentration of 2 molecules. The concentration of the nucleophile and the concentration of this alkyl halide. So that's where the name comes from. Now, do you remember when we did section 4 and we talked about if it has symmetry, it's achiral, and then if we are asymmetric, we're chiral, and how it's just flipped of what we would expect, and so it's like a little extra mental step to be like, okay, which one's which, and mashing it up. SN2 is 1 step compared to SN1, which is 2 steps. I hate it. I'm so sorry. And it's because this 2 comes from the rate law rather than like how many steps are in the reaction. Now, SN2, again, if the mechanism is pretty easy, what's the hard part? 2 things. 1, getting correct product stereochemistry, and then 2, figuring out which molecules are good candidates for SN2 reactions. So let's first talk about the stereochemistry. So Logan did the little demonstration with the little balls, right, and like the kind of magnets, and it like poofed off the leaving group. Love that. When we have an SN2 backside attack, let's look at where these groups are arranged. So we can use our like lecture 4 skills of assigning R and S of our priorities here, 1, 2, 3 clockwise. So this is R. But then when we do our backside attack, we start making a bond from the back and breaking the bond with the leaving group. And very briefly, this is this kind of trigonal bipyramidal geometry. So she right here is planar. But then once the nucleophile is there, we've kind of poofed out the feathers different. So like here, the poof was out this way. Then over here, the poof was out this way. Like we've gone from which side we are on. That's weird. And that's a little hard to kind of think about in terms of stereochemistry. So we can always fall back on our R and S assignment. So over here, our nucleophile priority 1, 1, 2, 3, now it's counterclockwise. So it's S. So we see we have inverted the stereocenter. So the Pavlovian conditioning today, it's not as great as I would like. I really spent time trying to workshop it and did not go well. Like I was trying to think about like parody lyrics to like a Chapel Roan song. Like, it didn't go well. I have an audio message of me at like 12:30 a.m. last night trying to be like, like just chance. It didn't happen. So bear with me. The call and response is not going to be as optimized as I like. So one of the first things that you should think when you're thinking about SN2 and how it happens is inversion of stereochemistry. So can we try SN2 inversion of stereochemistry? SN2 inversion of stereochemistry. SN2 with the emphasis, like SN2. Yeah, hit it. Now, like SN2. Ding dong, work. So one thing that I'm going to note here is, do you remember that tricky challenge problem that was like, they meant to form the S enantiomer, but instead we got the R enantiomer. What happened? That one, the big thing behind it was when the reaction happened, it changed priorities of some of the groups. So this inversion of stereochemistry works because typically the leaving group is something like a halogen is going to be first priority. And then where a nucleophile attacks, it's going to be something like an oxygen, and that's also going to be first priority. But things get a little bit weird if those priorities swap. Like if you like do a nucleophile attacking and it changes some of the priorities, you might not necessarily get inversion of stereochemistry. We have never asked a question on that, but it's just kind of like FYI, like this works for most cases, but this is like the fine print disclaimer of like if the priority changes, you might go from R to R. Very rare, we've never tested it, which means it could be a good test question, but no. So we're going to do a quick practice here. First part is just writing an SN2 mechanism. It should take 5 seconds. Second one is predicting the products here, and we're going to talk about a couple of different ways that we could write the product, but try to use your RNS assignment to check that you've done it correctly. For the third one, we've given you a product, and we've asked you to supply what a good nucleophile would be to get that, and then also what the starting molecule would be. So making sure to pay attention to the stereochemistry there. So I'm going to give y'all like 3 minutes. And I'll play some music. Let's talk about it. Also, I think I know everyone's name now. We'll see. We'll see. No, I was going through and I was like checking off. I was like, yeah, I think I know. There were only like 3 people in the class now that I'm a little iffy on, but they don't come to section. So here we are. Okay, first off, mechanism. We have OH minus, backside attack, kickoff. So easy. So easy. And especially if we don't have a stereochemistry. Hey, you know, they don't all have to be difficult. Now, predicting the product, 2 main ways of doing it. One way of doing it is thinking about like the actual geometry of this going and attacking from behind and then kicking it off. So if we do it this way, we're doing 1, 2, 3, 4, 5, and then it's kind of like our SCH3 gets added up here, and then it pushes the wedge and dash down, but doesn't change the wedge and dash. Like they both stay like methyl on the wedge, hydrogen on the dash. And let's check it with our stereochemistry. So over here, priority is 1, 2, 3. We do it clockwise, so it's R. But then over here, it's 1, 2, 3. And ooh, it's counterclockwise, so it's S. So did we do SN2 inversion of stereochemistry? Yes. If you are ever doubting yourself on like a test situation, which in the test situation we are going to give you the stereochemistry version, we're not going to give you the easy one, so sorry. It's always like great to bust out the RNS, and it's also good to keep it fresh because RNS is going to come back in the final. Yeah.
Why did we like add it on top instead of like
We're going to talk about it. So this is one way of drawing it, but I feel like when your molecule gets more complicated, it gets a little bit harder. So another way of drawing this substitution is put the nucleophile in the exact same spot where the leaving group was. But when you do this, you need to swap the wedges and dashes. So over here, now we are going to have the hydrogen on a wedge and the CH3 on a dash. So now we can trace priorities 1, 2, 3. It's clockwise, but our hydrogen is coming towards us now, so we're in opposite day. So it's going to be S. These are kind of the 2 main ways of drawing products for SN2 to show the inversion of stereochemistry. I like method 2 a little bit better. Like, I think it's just easier to think about swapping it. But that's just me. So now, what part of this third molecule looks like it was probably a nucleophile that didn't attack? Yeah, it's like CN over here. So how should I write that as a reagent? Should I just do CN? NaCN. Because we want it to be CN minus to be a good nucleophile with that negative charge. But then we like to put a counter ion with it just because that's how it's going to exist when we grab the flask or beaker or whatever that has the reagent. Cool. So we have this, and we need to have some sort of alkyl halide with a leaving group. So I'm going to do it the method 2 way, where I'm going to write the leaving group where the CN currently is. So here, pick your favorite halogen. I just did bromine. There's no reason. And then when we do it this way, where it's in the exact same position, we need to swap the wedge and dash. So I'm going to put the methyl on a wedge, hydrogen on a dash. And we can check with the RNS, but I will leave that as an exercise to the viewer. Cool. So yeah, with this kind of inversion of stereochemistry, you can think about it, it's the same trick for going backwards and forwards of just put the thing that you are substituting in the right place and then switch the wedge and dash. Yeah.
Can we make our leaving group anything, and if it's a bad leaving group, it's just going to be a really bad yield?
Yeah, have fun, but not too much fun. That's kind of the vibe. Yeah, if you can do a leaving group that's a solid leaving group, sure, knock yourself out. If it's going to appreciably change whether the reaction happens, we would have to count off points. So when in doubt, go with bromine. Cool. So that's kind of this first little practice. But now let's get into that second question after the stereochemistry of factors affecting SN2 reactivity. So there are 3 ones that you talked about in lecture, but the main one that's important is sterics. So when you're thinking about whether or not SN2 is a good reaction or these molecules are good candidates for SN2, you should be thinking sterics. So can we try another SN2 column response where I say SN2 and you say?
Sterics.
Cool. SN2!
Sterics.
SN2. Good.
We're saying
Good.
a single word.
Good. Yeah. They're sterics. Like maybe that's my interpretation, but good. So SN2 sterics, SN2 inversion of stereochemistry. And again, I was trying to be like, how can I have one prompt be 2 column responses? And then I'm like, this undermines all of operant conditioning. Like this is not going to work. And that was like maybe a song. Yeah. So this, I like the page that Logan showed in lecture where it shows you the like target that the molecule is trying to attack, and how when you have more like substituted carbons here, that target gets smaller and smaller. So when you have a methyl, your nucleophile has basically no barrier, and it's really, really fast for SN2. Same for SN1. Your backside attack is going to be really easy. But tertiary, this carbon is so blocked by the other atoms and the electron clouds that like SN2 just doesn't happen. So this is going to be the major factor that affects SN2. Leaving group ability, we talked about like stability and like PK, blah, blah, blah. Yeah, this I'm mostly having here for reference. It is a factor, but like it's not going to be a huge factor. Nucleophilicity, maybe I'll talk about briefly. Nucleophilicity, which one is like, wow, made up word. But second, it's just this kind of way of like measuring how likely something is to be a nucleophile. And the thing that is cool about it to me is it's not just about having a high energy donor, it's also about kinetics. So like to be a nucleophile means doing a specific reaction, and you have to be able to access whatever your acceptor orbital is. And so if you have a really bulky group on your molecule, you're not going to be a good nucleophile, even if you have a high energy donor. And the epitome of this, an iconic figure that I would like to introduce formally, is Miss tert-butoxide. Now, tert-butoxide, she has this tert-butyl group that has all these hydrogens on it. It's going to be super, super bulky. So do you think that this is going to have an easy time accessing electrophilic sites? No, it's not going to have an easy time. Mostly because, like, imagine it has to get into, like, a tight squeeze between these other, like, methyls that all have hydrogens. And this, I'm doing it with attacking carbonyl, but you could do it with an alkyl halide too. Like, this is going to have a hard time getting in there and attacking. And so we would say it's a poor nucleophile. But in terms of base strength, it's still an OR minus, which is about the same as like an OH minus in terms of base strength. And that's a really strong base, like hydroxide, strong base. When you did like basicity in Gen Chem and you were talking about like Ka and KEQ, that's related to like the delta G of a molecule. That's related to thermodynamics. And so you have this kind of scale of acidity basicity that's based on thermodynamics and stability, and then nucleophilicity that has this kinetic component. And those are kind of separate scales that we can rank molecules with. And so this is pretty, I was going to say I think it's the only molecule that you will learn in this class that is a strong base, but a poor nucleophile. And so it's going to subvert a lot of our expectations and a lot of the rules that we have. So its energy to me is Bigay Ducrine. It's like, let's mess with it a little bit. Let's go the road less traveled. Let's mix it up. Chaos. Ooh. And she's going to come back. And so we want to like have her in our mind as something to use when we need to do kind of exception things. Or something to look out for as like, oh, this is going to be a little troublemaker for SN2 if we try to do it. She also has some fun like secret spy aliases. So you can write her out fully like this. I like this one because it's Kotbu. It's Kotbu. It's so cute. Kotbu? No? Okay. Like, have y'all seen our good friend Naomi? I love them. Or Naomi, sometimes at the end of the day, she needs to grab a proton, and then she goes home. Again, I love the little names. Also, this version's like, what's the T? Okay. Whatever. She's an iconic figure. You should know about her. So that's why I spent 2 minutes on it. With that, we transition away from SN2. Our big takeaways are inversion of stereochemistry and sterics. Let's do another transition. Elimination. What? That's from Hannah Montana. Thank you. Wait, are y'all again, now I'm getting like older in age from y'all. So did y'all didn't grow up with Hannah Montana, but you heard of it, right? Okay. Were other people watching Hannah Montana?
Well, like I think like they would just like if you watched cable, like it would just like
It's-
was one of
she's
those
still
things that
there.
They would play replay. Like
Sure, it exists.
But then again, like in 5 years, there are going to be students in this class who did not grow up with TV on TV. Like they grew
Yeah.
up with just Hulu, you know?
mhm.
So I don't know. All my references, like I can only teach organic chemistry for a limited window, and then everything will be gone. It'll be gone. So E2, we are now in the realm of eliminations. Elimination reactions are other big type compared to substitution. Eliminations eliminate a leaving group, and then they create an alkene, a carbon-carbon double bond. So one kind of tricky nomenclature thing that like can cause some issues is, do you remember in lecture in section 5 we talked about alpha carbons, alpha hydrogens related to an amine. So we said if we have our amine here, the carbon next to it was alpha, the one away from that was like beta. And this, we did things like alpha protonations, alpha deprotonations. So love alpha beta, she comes back, she's going to come back later as well. But it's a little annoying because over here with the amine, we started talking about the alpha at the carbon next door to the CN double bond. And over here for the alkyl halide, it's literally the carbon attached to the bromine. And so it's just like a weird nuance of like how we label the alpha beta here, where for alkyl halides, the alpha position is going to be what's directly attached to the bromine, and then beta is going to be one away. Now, this matters, this nomenclature, because our reaction mechanism is a base is going to come along, and it's going to deprotonate at the alpha beta position here. So it's going to deprotonate a beta hydrogen. The electrons in here will fold in, create a double bond, and then kick off the leaving group. So it's E2 because E for elimination, 2 for second order rate law. It depends on the concentration of our base and of our alkyl halide. Now, this is another one that's going to be hard to chant, but there is this stereochemistry requirement, or like 3D arrangement of the geometry in order for an E2 reaction to happen. It's a little bit like Princess and the Pea of like, we need princess treatment here in order to get E2 to actually occur. So what the requirement is we need the electrons in this sigma CH bond to directly overlap and be parallel to the sigma star carbon leaving group orbital. Because we know this reaction is going to be breaking this carbon leaving group bond, so we need to put electrons in that antibonding orbital. And this reaction just essentially won't happen unless these electrons are lined up, so it can just slide the electrons right over and break the bond. So when we do this, if we did a Newman projection of our eye here looking directly at it, our leaving group would be straight up in the front, and our hydrogen would be straight down in the back. This is our anti-conformation for the leaving group and the hydrogen. We can also think about these 4 atoms of the 2 carbons that make the double bond, the leaving group and the hydrogen, as being in the same plane, like the plane of the page. So we would say they're periplanar. And so our geometry requirement is that the beta hydrogen has to be anti-periplanar to the leaving group. And so Pavlovian conditioning, one of the things that you should think about when you think about E2, how it happens, is anti-periplanar geometry. So can we try? I say E2 and you say anti-periplanar geometry. Now do it like a little snoot. E2, anti-periplanar geometry. E2. A little bit louder, excitement. E2. E2. Work. Cool. So, again, it's a little annoying, princess treatment, but it's required. Oftentimes, we don't have to think about this a lot because molecules that are like straight chain, they can freely rotate. So it's not a huge deal. But and the other thing, after we do this kind of geometry reality check, the main factor affecting whether or not we do E2 is base and basicity. One note on geometry, let's look at this example here. So I'm going to ID, we have the alpha position, we have beta positions here. Why does this not do, well, I have the answer written on the board. Why does this not do E2? Well, we don't have any beta hydrogens. So if we don't have any beta hydrogens, there's nothing that we can deprotonate to make a double bond and kick off the Cl. So there's no E2 reaction. So always have this kind of reality check in mind of can you do E2. For basicity, we use the pKa values that you have like memorized now as our kind of benchmarks. So we say something is a strong base if it's OH minus or better in base strength. Typically, these are O's with negative charges, carbons with negative charges, or nitrogens with negative charges. Then we say fair bases are between OH minus and H2O in base strength. This is going to be things like ammonia or just any amine that's like neutral. Cyanide, acetate, those are all going to be fair bases. And then weak bases are going to be H2O or worse. So like water, alcohol, any of these kind of neutral molecules. If we had something that was like an acid's going to be, in this scheme, a weak base. Because it's an acid, it's not really even a base. So we would just say it's poor.
So like the chlorine anion would count as a like weak base here. It would be worse than like
Yeah.
HCl would be -6, therefore Cl minus would be
Yeah. But honestly, that's a little bit more than weeds than we'd ever ask you. But yeah, that's the extending the like logical conclusion. One thing I do want to flag here, and this tripped people up in lecture a little bit, it trips people up every year. Don't let it trip you up on the test. It's so painful to see. We need to talk about the difference between an alcohol and an alkoxide. So an alcohol is neutral. It does not have a charge at all. And so it is not going to be a good nucleophile. It's going to be a poor nucleophile. And it's going to be a weak base. Because like it's essentially like water, like H2O in terms of reactivity. Water you can put on your skin. Ethanol, rubbing alcohol, you can put on your skin. So very mild, not going to be good at SN2 or E2. But alkoxides? She is OET minus, negative charge, build up electrons, high energy donor, ready to pounce. So an alkoxide is going to be a good nucleophile, and it's also going to be a strong base. With the one exception of BK do crime. That is still a strong base, but it's a poor nucleophile. So do you feel like you understand the difference between an alcohol and an alkoxide? Trepidatious, but work. Cool. So now we have several questions when we are doing an E2 reaction to figure out like what our actual product is. So over here, if we look at the alpha beta positions, we have 2 beta hydrogens on the left, 3 beta hydrogens on the right. If I knew nothing about chemistry, I'd be like, probability. It would be more common to do a deprotonation over here just because there are more hydrogens. Sure. And so you would think that this terminal alkene, the one on the end, is going to be very favored. But this old dude named Zaitsev spent his whole like PhD or postdoc or whatever saying that actually that's not the case. So it has to do with the stability of alkenes being made. We can describe alkenes as being more or less substituted based on how many non-hydrogens are on it. So like here, we would say this is totally unsubstituted as an alkene because we have no carbons, all hydrogens. And as we add carbons on to replace the hydrogens, our alkene gets more and more stable thermodynamically. And so that is just a result that we are going to use to help us understand why we form certain alkenes. Also, I say Zaitsev, and I think Logan said Zaitsev. I don't know, but I don't think either of us are going to change. So pick your favorite. Choose your teams. I will be judging. So what we actually have in terms of our percentages here is our terminal alkenes only going to be 25%. Whereas our internal alkenes are going to be more like 55%. So we get way more of these internal alkenes, and it's because terminal alkene, this one over here, has 3 hydrogens on it, whereas these internal ones only have 2 hydrogens. So these internal ones are more substituted and more stable by Zaitsev's rule. Now, between the trans and cis, which is more stable? Trans. It puts the steric bulky groups opposite of each other. So we get 41% trans, 14% cis. The actual percentages don't matter. It's more about the trends. So our kind of big upshots here are Zaitsev's rule. Internal alkenes are more favored than terminal alkenes. And then 2, among internal alkenes, trans is more stable than cis. So that's the rule. But because this is organic chemistry, nothing can be easy. And so we need exceptions to the rules. And who is doing the exception? None other than Kotbu, our Bigay du crime, mixing it up. So normally, if we just had like OET minus, this is going to do an internal alkene formation here. So it's going to grab one of these beta hydrogens and then make the alkene internally because that's the more stable product. But when we have our dear friend Kotbu has all these like hydrogens on it. And that makes it really, really bulky. So if we have the choice between grabbing hydrogens that are in the middle of a molecule versus hydrogens that are on the very tippy end, it's going to be easier for Kotbu to grab one on the very end. So we pluck it off, make a double bond, kick it, and then we get the terminal alkene as our product. So this is a helpful tool for if we specifically want to make that terminal alkene, which we call the Hoffman product. Hoffman was a chemist. And fun fact, one of the organic chemistry professors here, who if you take 27, it'll probably be taught by Serenia. She has taught this course partially in the past. She teaches a lot of organic chemistry here. She studied with Hoffman. Like, and I was like, dang. Apparently he was teaching until his like 80s or something. But yeah, like I'm 1 degree of separation away from Hoffman. Y'all are 2 degrees. So I'm happy to be that degree for you. Cool. Yeah. So bulky bases favor the Hoffman terminal product. The last thing that I want to talk about with this practice here has to do with what if we are trying to do an E2 and we are on a ring. This is something that's not really tested as much in other classes, but we really like it because it combines a lot of skills. So the big takeaway is if you are trying to do E2 in a ring, you have to draw chairs. And for now, what I want you to do is take this molecule here. I want you to draw the 2 distinct chair conformations for it. One of them where the bromine is going to be up axial, and one of them where it's going to be up equatorial. So take a minute and write out those 2 chairs. And then I will do the same.
So according to the Russian pronunciation YouTube channel, it's Zaitsev.
I mean, no, I'm out here doing German diction and singing Lieder, and I'm like, I think it's Zaitsev. But then if you do it in real German, it's Zaitsev.
No, but I thought it was Russian.
Oh, it might be.
Like, yeah.
No, that would make sense. In that case, I have no idea. Wait, Evrim, are you Russian? Do you speak Russian? Okay. Work.
Sandra's Russian.
Sandra, I need to ask Sandra.
On Friday.
Work. Okay.
Wait, here, I can just ask her.
The other thing that I want you to do when you're drawing your chair, I want you to draw all beta hydrogens on the chair. So find the beta position and put the hydrogens there.
So basically, when they ask us this question about like what is the major and minor product, if we have an E2, so we put our major as the trans, our minor are the terminal, the cis, and the SN2.
So this is the thing. We typically will not ask for minor products because there can often be so many with all the E2 ones. Because like you could also be like if SN2 is in the running, like one of the things, where is this? One of the things up here, we only got, what is that, 80% from all these. What's the other 30%? Substitution. And so, like, yeah, like, do we actually want you to draw the transalkane and then draw 3 other molecules? No, we're not really going to ask that. And so typically it's mostly just about writing what the major product is.
Okay, because like
Yeah, it'll get too hard too quick. Yeah, totally. So let's look at these chairs. Okay. So this is our kind of like exam 1 skill coming back. How did you do with your chairs? Or how did I do? Because I was talking while I was drawing them. So, left or right, like, or option 1 or option 2? Which one is the more stable chair? 2, right? It has everything equatorial. More stable. Less stable. But the interesting thing here for E2 is, in order to get an anti-periplanar geometry with a hydrogen that's in the ring, both the hydrogen and the leaving group have to be axial. So, like, do you see how this isn't anti-periplanar? This isn't anti-periplanar. This is not anti-periplanar. It looks like maybe it could be, but this one goes up and this one goes down. Like, it's not anti-periplanar. So this, and I'll kind of like highlight 1 or 2 of these. Bum, bum, bum. Bum, bum, bum. We would say this conformation is not E2 reactive. So if the molecule is sitting like this, it will not do E2. But when we go to our less stable chair, suddenly we have our leaving group axial. So which of our beta hydrogens, 1, 2, 3, which of these are we going to be able to do E2 with? 2, because it's the one that is axial here. So that is anti-periplanar geometry. And again, the only reason we have to think about this is because we're in a ring, we're constrained in our conformations. Normally, if we're in a straight chain, we can rotate freely all day. And so this conformation is less stable, but E2 reactive. And so that's a bit of nuance. Ooh. Like, hey, if we want to do this reaction, this molecule is going to spend most of its time in this more stable chair. But in order for a reaction to take place, it has to go to a less stable chair in order to form a product, which will ultimately be more thermodynamically favorable. So again, the problem set's going to tease out a lot of that. But what that means is our product over here is we're going to make our double bond up that way, because that's where the beta hydrogen that we could access and do E2 was. It was not on the side that had the methyl. So, notably, this does not follow the kind of really simple Zaitsev's rule, where like this alkene looks more substituted, but it is just impossible to get to on a chair. So, that nuance, again, is going to come back, and I think several challenge problems. Like, there are 2 or 3 where you're going to be doing stuff with this. Cool. That's all I have for E2 for now. Can we do another hard pivot, and then we'll do GFP, kind of putting it all together? Let's see what this transition turns out to be. That was from That's So Raven. So last family is the SN1 and E1 reactions. So SN1 and E1 are substitution and elimination, just like we saw before, but the key thing is these proceed through a carbocation intermediate. So the rate determining step for both of these reactions is this first slow step where imagine you are a leaving group, you are in this bond, y'all have been together for a while, and you said, it's just not working. I'm going to take my electrons, I'm going to head out. And you know, sometimes that can be a positive thing. I don't know. But this you've never really seen before. You've only seen the dramatic lone pair push of like pushing someone else. This is just like, hey, it's been real. I'm going to peace out. And the main thing that determines whether or not we can do that, just leaving group leaving, is how stable our carbocation is. So we'll get to that in a minute. But once we are at our carbocation, we have an MTP orbital. So with this, our nucleophile could come in and just straight up attack the MTP orbital. We would get our substitution product, our SN1. Or we could have a base come along and deprotonate a beta hydrogen here, fold in, make a double bond. We have E1. So these, like 1, come from the fact that it's a first order rate law, in that the rate of the reaction only depends on our concentration of our starting material, like the alkyl halide. And it's because that's the slow step, the rate determining step. But again, remember, E1SN1, it has the 1 in the name, but it is 1-2 steps. So it gets a little hairy. Cool. So let's talk about the carbocation and like how we stabilize it. So, do you remember a thing in PSET 2 and 3 where there were some questions on the skill builders where essentially you just had to know that alkyl groups like a methyl are electron donating, and we didn't really explain it. This is the thing we didn't explain. So this concept is hyperconjugation, and I like a couple of metaphors with it. So I imagine a carbocation as a disaster, like someone's house burned down, and like this is the site of the house burning down, the carbocation. If we go one next door, this is a neighbor, and they have some electrons here, and hyperconjugation is the neighbor going, they're there, it'll be okay. And it's mildly stabilizing for carbocation that needs electrons. It's also kind of like leaning its electrons over just a little bit. But it's a very much like you're having a disaster. I'm so sorry. It keeps it kind of at an arm's length. But then when you have 3 of those, okay, like 3 people have said they're there. Your house still burned down. It's still unstable. But once you get 6, you're like, maybe I'll survive this. Once you have 9, it's my community is rallying behind me. My house burned down, but I got 9 theirs from all these neighbors. It's going to be okay. So tertiary carbocations here, pretty darn stable. More so than you would expect. There's actual like MO explanations with like donation of the sigma bond into the like 2PC, lowering the, but like that's not memorable, and so I like the theirs. It also, to me, hyperconjugation is kind of the reverse idea of induction. So induction, we talked about certain elements on a molecule tugging electron density away, and it could help spread out a negative charge, for example. So if induction's kind of pulling electrons a little bit away, hyperconjugation's doing the opposite. It's leaning them a little bit towards. So both of those ideas, I think, are really like helpful for me. Now, hyperconjugation is one way we can stabilize a carbocation, and that's the neighbors they're-thering. The other way is resonance. So resonance says, hey, you have a positive charge, I have a positive charge. Let's take this on together. We're going to spread out this positive charge. We all got this. It's like instead of one person's house burning down, it says, okay, I'll take some of the fire and burn down part of my house, so then part of your house is left over, which is the logic of this metaphor. So like we have a resonance structure here where our positive charge is over here, and we are literally spreading out the positive charge over multiple atoms. So this, when we have resonance, it's going to be comparable to like tertiary carbocations in terms of favorability for the reaction. We give her a special name, like this position next to a double bond is called the allylic position. You don't need to know the names, but again, sometimes the names are helpful. It's also giving ally, like I'm going to help out with this positive charge. And then we also have this position next to a benzene ring called the benzylic position, and she has a lot of resonance. She's out here resonating, spreading out the positive charge over like 7 atoms. So great. Ride or dies, taking on the positive charge with you versus hyperconjugation, theirs. Another one that's kind of unexpected is if we have a carbocation adjacent to something with a lone pair, we have a resonance structure where we have a complete octets on every atom, and that's big. So that's going to be one of the most stable like carbocations that you can get. Cool. So these are our like main ways of stabilizing. Yeah.
Like, so when we thought about like electron donating groups and stuff per se, like, is it like the same deal where it's like if you connect a better like electron donating group to like a part with a positive like charge, it's going to be better?
Yeah. Like if you have, and the charge has to be positive for that.
Yeah.
Like if you are donating electrons towards a positive charge, it's stabilizing. If you're withdrawing electrons from positive charge, destabilizing.
Yeah. But like, which one would be better? If you had like just a methyl attached to it, or if you had this like big long carbon chain?
It doesn't matter because it's about the sigma bonds. So like whether or not this is a methyl or if this is a like long R group, this is a sigma bond. It's the sigma bond that does the hyperconjugation.
Okay, so
there
the
is
additional ones aren't really
Yeah, further out doesn't really make a difference. There is a very slight difference between the donation between a sigma CH and a sigma CC, but like that's beyond the scope of this class.
Which one would be better though?
I think sigma CH. I don't remember why, but I think. So, yeah.
Like for the 9 times, sigma CH.
Yeah.
Or it's the 3 methyl groups
Yep.
around the
Mhm.
carbon. If one of those was an alkene, would that ever be a good leaving group?
Like this?
No, like if one of those methyl groups was instead an alkene, so it's like a double bond, and there was.
But would the double bond be here?
Yeah, but so it's a neutral charge. Would that ever be a good leaving group because it's so stable? Like, would you ever see like the double bond go away?
Oh, you're talking about like if you had like something like this and the leaving group left and
no,
make.
no, just all carbons. So like.
Then it wouldn't have a positive charge because it would have a full octet.
No, exactly, but because it's like stable with the positive charge, would you ever have the alkene?
But there's no
turn
positive
into-
charge.
So, I'm saying, would the like double bond ever, go and take a hydrogen from somewhere?
Oh, that is lecture 8. Yeah, you're asking about the reactivity of alkenes, and like that's lecture 8.
Okay.
So yeah. Thinking about the right thing, but I was truly like, there's not a carbocation. What are you? Yeah, sorry. Cool. So that's carbocation stability. A couple of like odds and ends here to talk about. So when we have this empty p orbital carbocation, what is the hybridization of this carbon? sp2. The reason is we have to have a pure p orbital open for the carbocation, like the empty orbital. She's going to be a pure p, so we're only mixing together an s and 2 p's, so sp2 hybridized. And if this is sp2 hybridized, what's its geometry? It's trigonal planar here, so all of these are flat, and then the p orbital is perpendicular to it. Now, if our nucleophile is coming along to do SN1, it could attack the top face, or it could attack the bottom face. And depending on which face it attacks of that p orbital, because we have the lobe above and below, we're going to get 2 different enantiomers. So whereas SN2 was very specific, you always had SN2 inversion of stereochemistry, SN1, oftentimes you're going to get a racemic mixture of the R and S isomers here. Because this is organic chemistry and nothing can be easy. There are ways that we can like mess with that. So imagine this. We have Cl, it leaves, make this carbocation. We have a big isopropyl group on a wedge on the top face of this molecule. We also have a methyl up on a wedge. Do you think a nucleophile is going to do better attacking from the top or from the bottom? When I say the top, I'm talking about like the side with all the wedges, or the bottom is going to be the side with dash hydrogens. The bottom one. So here, and again, it's a little hard to imagine just because there's so much here. Imagine the molecule is like flat here, and then you have big bulky groups up top. The nucleophile is going to want to come from the bottom because it doesn't have the bulky groups. And so if our nucleophile was like water and we added an OH here, it would only add from the bottom. Even though we just said, hey, p orbital, you could attack either side, this is a molecule where it's going to strongly prefer attacking from the bottom. We've never asked about that. Like, maybe there's like 1 or 2 like problems in the P set that like explore that just like conceptually as an idea. But for the most part, SN1, you're thinking about a mixture of R and S. For E1, generally speaking, you're following Zaitsev rule in the same way. Now, we've grouped all these together. We've said SN1, E1 together. They both have the same slow step. So typically, if you can have SN1, you can also have E1 happening. And generally speaking, when both of them are possible, SN1 wins. And it really is just because SN1 is faster. It's much easier for 2 molecules to randomly bump into each other than to have like the princess treatment alignment of this sigma CH with the p orbital and this base come along all together. Like that's just a little bit slower. So most times SN1 is going to win between these 2. And that can be your assumption generally. you can mess with it a little bit. Again, because organic chemistry, you can always mess with it. And other classes do this a lot more. We do not really do this much, but one way to get more E1 product is to use a higher temperature. That's going to favor E1 because that product's going to be more thermodynamically stable. But we essentially now need a strategy where we're guaranteed E1. So our strategy is we got to conk it. So this strategy is when we have a secondary or tertiary alcohol, not alkyl halide, alcohol, with concentrated H2SO4. So this is sulfuric acid. So the first step is she's going to protonate OH. Now OH alone is not a very good leaving group, but once she's OH2+, she's ready to hit the road. She said it's been great. Thank you so much. I also, after teaching the 8:30 a.m. section, I was walking and getting a latte. And I said, I need a, little stepping song. Do you know, this song, the Jordan Sparks, I was thinking about that as I went to go and get it. And I was like, oh my god, that's like a TikTok sound of someone being something unacceptable just happened, and then they're leaving. They're just walking out. That's a leaving group. That's the leaving group leaving. That's SN1. That's E1. Here we are. But here, the leaving group leaves. And then we are left with this carbocation. And the only other thing really in this mixture is the conjugate base here. Now, sulfuric acid, strong or weak acid? Strong. Sulfuric acid, you do not want sulfuric acid thrown on you or whatever. So strong acid, then this conjugate base is going to be what? A weak conjugate base. So in terms of GFP, this is going to be pretty poor as a base. But it fully won't act as a nucleophile. And it's because there's so much resonance going on over here, and because we have our expanded octet, she just doesn't act as a nucleophile. And so in the absence of anything else, it will act as a base and do this deprotonation and get our E1 product exclusively. So when we conk it, SN1 is not an option. We only get our E1. So I have a very quick practice before we jump into the full GFP stuff. So in your head, not allowed, I want you to look at this, touch the earth, and say, what happened? SN1 or SN2? Be thinking about it, and in a minute, I'm going to ask for evidence for the jury. So look at this, try to figure out which happened, SN1 or SN2. Does anyone have any evidence they would like to share with the class? Yeah.
Is it SN2 because they're both fair?
Not what I'm asking. I appreciate it, but that's if you're trying to predict the product. I'm saying we have a product, so we will be able to know. But there are a couple pieces of evidence hidden here that tell us that this is one or the other.
Is it SN1 because there's no inversion?
So that's one of our first pieces of evidence. Over here, have y'all seen this plus minus before? I think it's been listed a few places, but maybe we haven't talked about it enough. Plus minus means that we have a racemic mixture where we have both the enantiomer listed and we have the version of it on a dash. It's essentially just a shortcut for us to not have to write two separate molecules. So if you see a plus minus, that means you have this molecule, you also have the version with swap dash and wedges. So if we have a mixture of stereocenters, like our R and S, that is going to be giving us evidence towards SN1, where we have an MTP orbital we could attack from either side. Whereas SN2, we always have one stereoisomer for the product because we're doing a specific inversion. What's another piece of evidence that we might have done SN1 versus SN2?
Is it the resonance stabilization from the ring?
Ooh, there are three pieces of evidence. Yes. We are right next to a ring. And so if we had this positive charge, that's going to be a benzylic positive charge that's right next to the ring, lots of resonance. So great. This is giving us SN1 as well. There's one more piece of evidence.
Weak base.
Yes. So This is an alcohol. Are alcohols good nucleophiles? No. So that's not going to really want to do SN2. So this is a poor nucleophile. Compared to like OME minus, great nucleophile. Great nucleophile, great base. So this is our third piece of information of this is an alcohol. Bad nucleophile. So this is saying kind of not SN2. So picking up on those like different pieces, I think is going to be important for putting it together. I do want to move on, but then we're going to have time where I'll circulate and answer more questions, okay? So putting all of this together, we have the GFP system, which kind of gives you an algorithmic approach for how to assign which is the major product between all of these different options. So the main thing for SN2 is sterics. The main thing for E2 is base strength. And the main thing for SN1 and E1 is carbocation stability. And those need to be the kind of immediate assumptions in the first line that you are checking, like is going to give you the answer 90% of the time. We also need to think about the other cases, but for SN2, steric-wise, if it's a methyl or a primary for the electrophile, we say it's good. Secondary, it's fair, and poor if it's tertiary or if the nucleophile is bulky, like our COBU. Then for E2, base strength. So good base is OH minus or better, so that's also like an OR minus. Fair is between H2O and OH minus, and poor is H2O or weaker. And for SN1 E1, it's about the carbocation stability. So if it is tertiary or better, like resonance stabilized, that's good. Secondary, fair. Tertiary, or primary or methyl is going to be poor for carbocation stability. Now this is the kind of base of the algorithm, but in order to not miss questions, we have to add in some other checks. So a couple of quality assurance checks. One, the nucleophile vibe check. Is the nucleophile a good nucleophile? Or is it like an alcohol bad nucleophile? Or is it a bulky nucleophile like butoxide, things like that? It can knock down the favorability that we determined up here with just primary, secondary, tertiary. The other one for E2 is reality check. Do we have a beta hydrogen? Could it be antiperiplanar? So another one to think about. And when we are doing this system where we're kind of simplifying a lot of the things, we're going to get a lot of situations where they're going to be ties, so we need a tiebreaker. The tiebreaker is going to be based on just kinetics. SN2 is faster than E2, is faster than SN1, is faster than E1, with all other things kind of equal. So let's do a couple of these together to just think through the kind of algorithmic approach. Starting off with SN2, the main thing that we are looking for SN2 is what? Sterics. So SN2 sterics. So we look at our alkyl halide. Is it primary, secondary, or tertiary? Primary. So is it good, fair, or poor for SN2? Good. We do our vibe check of the nucleophile. Is this a good nucleophile?
Yeah.
Great. Okay, moving on. Then for E2, base strength. So our base here, are we a strong base or a weak base? Strong. We are OME minus. It's like an OH minus. So this is a strong base. So are we good, fair, or poor? We're good for E2. SN1 E1 is about the carbocation stability. If we did a carbocation here, it would just be a primary carbocation. Good, fair, or poor? Poor. High poor. So between these, we look and we have a tie for good. So who wins? Well, the faster one, SN2. And so to draw our product, we have our carbons there, and we are going to put our OME substituting for our leaving group here. Let's do one more together. So let's do 6D. So 6D, for SN2, are we primary, secondary, or tertiary with our leaving group? We're secondary. So this carbon right here is attached to two other carbons. Secondary, so good, fair, or poor? Fair. But if we do our nucleophile vibe check, do we have a good nucleophile? No, this is an alcohol. So it's a bad nucleophile. So it's semantics what you do here. Some people would say, okay, F minus. Or you could be like, actually, I'm going to demote that to poor. Like, that's kind of generally what to think about. It's worse than fair somehow. Okay, E2. An alcohol. Are we good, fair, poor, base strength? Poor, because this is an alcohol, not an alkoxide, the negative charge. So this is a weak base. So another high poor. Third one, SN1 E1, we look at the carbocation. So the carbocation that we would form, where did we go? Primary, secondary, tertiary, well, secondary. So is it good, fair, or poor? Fair. So in this case, the fair wins out. So we are going to be doing SN1. And again, generally for this category, it's always going to be SN1 unless we're trying to conc it. So for this, this is the other thing that trips some students up sometimes. For ETOH, what are we going to put here when we do our SN1 substitution? Are we going to put OET or OH? We're going to do OET. And the reason is because it's a lot easier to take off a hydrogen from an oxygen than it is to take off a carbon. So when this thing comes and attacks, you're going to have an intermediate that has this OH and a positive charge, and then you're just going to have it be deprotonated, typically by what you kicked off, the OTS. Cool. So I'm going to give y'all, like, let's say 10-ish minutes to look at these. These are Skill Builders, page 5 through 7. 5 and 6 are kind of more basic or like more straightforward, and then 7 is a little bit more involved here with some kind of exceptions. So I'll put on some music, let y'all work, you can talk together, and then I'll circulate, and then we'll go over in the last like 10-ish minutes.
So whenever I look at the word carbocation and want to pronounce it carbocation.
You gotta curb that impulse. Carbocation won't fly here. Thank you. Thank you. let's check this first batch, and then I'll move it and check the second batch. If you got something different, then can you ask about it? Because I think other people probably also did the same mistake.
For the second one, I put mine in the middle, but I'm seeing it because it's a bulky reagent. It would go on the terminal.
That, but also, it actually, this is the alpha carbon here, and this is beta. So actually, this is your only option for where to place it. Like your double bond always is formed between the alpha and beta, and we only have one direction. Yeah. If the iodine, instead of being there, if the iodine was here, then you'd have options. But because it's on the end, you don't have an option really. Yeah. Yeah.
So I know we like did 60, right? But like, the thing I'm thinking about is like, would the fact that it like ETOH like kind of sucks as a base not make that an F minus? Or,
Yeah.
like,
So I forgot about this because this is the key I wrote out last year. So this is where like ETOH, it's not going to be as big as like a really bulky group and demoting it, but it does demote it some. And here it's making it fair, maybe fair minus. But when you're in this toss up between SN1, SN2, that's when it comes down to some like solvent effects and things. And generally speaking, for us, we're not going to get into solvent effects unless it's explicitly listed. And so we're just going to go based on the kinetics and say SN2 wins. It's kind of going to be a toss-up. In this case, the product of both SN1 and SN2 looks the same. And so, yeah, it's one of those cases where there's a little bit more like nuance going on, and this system kind of glosses over it. So thanks for clocking that. Yeah, when I did it earlier, I think I just demoted this to poor, didn't I? Yeah, apologies. Let's look at the other section up here. So, any of these that people want to talk about?
5.2.
Yeah, it's a rough time out here. So,
why doesn't that one get like?
for this, we have CH3 methyl. So we would think it's good, but we have a bulky nucleophile. So if we're just going based on like the system of rules, bulky nucleophile here, we put in poor.
And is potassium like sodium?
Yeah, it's just a counter ion. So this is a minus. Then, why is it not applicable for E2?
It's not.
You don't have the beta.
As Chantel in the mid 2000 pop song said, it's like we just don't have anything else. We can't make a carbon-carbon double bond here because we only have one carbon. So, and then for this third one here, we're looking at this carbon with the leaving group. It would make a CH3 like a methyl carbocation. Not going to happen really. So the only option is our SN2, which is not very good. And so that's the product. But generally speaking, we would expect this to probably have some bad yield. But you can get into more nuance. Like, more nuance could be like, this is the best possible electrophile you could have for SN2 because it's methyl. It's not even primary. And so this being a bulky like nucleophile shouldn't matter as much because this is such a good electrophile. But I'm kind of wanting to show like if you just do this system of algorithm, what does it get you? And it's pretty close to the right answer. And most of the time it will get you directly to it, but sometimes there might be a little bit more nuance involved.
Why did you write low-key NA next to the poor if that was like the winner?
Wait, where?
In 5.2 you wrote low-key NA. Is that what that is? Oh.
Sorry, yeah, that's just my handwriting.
That's not bad.
But yeah, a low-key NA work. And then I'm going to scroll down just a little bit. Any others in this batch before we do page 7 together? That face says confusion. You said
No, I was just looking at 5.10, like I put OH instead of ON.
Yeah, that's the thing of like, it's going to be much easier to kick off an H here than it is to kick off an OC. And it's a really common mistake. A lot of students do that when they first start. Cool. Well, let's try to do these last few together. So, here, this molecule, our alkyl halide, are we primary, secondary, or tertiary?
Secondary.
Secondary. Cool. So, SN2, good, fair, or poor? Fair. And then vibe check, we have a good nucleophile, so we're good. Now, E2, base strength, good, fair, or poor? Good. We have OH minus. We're great. SN1, E1, at this point, secondary, so it's fair. So E2 wins. And now we have to clock. We're doing E2 on a ring, so what do we have to draw? We have to draw a chair. And specifically, when we did the exercise earlier, we drew both chairs. But now that you know the fact that that leaving group has to be axial, let's just draw the axial version. So in the axial version, bromine is up, and then that's going to make this methyl equatorial. So we have 1, 2, 3 beta hydrogens here. And so we have potentially some options. But remember, our beta hydrogens need to also be anti-periplanar. So can you tell me on your fingers, not out loud, on your fingers, 1, 2, 3, which of these is not anti-periplanar to our leaving group? 1, 2, or 3? Work. 1 is not anti-periplanar. So that is just, it's not the anti-conformation, whereas these are both going to be anti. So we have options. We can do it either way. We confirmed that by doing our chair structure. So given that, do we want to do the double bond that's this way? Or do we want to do the double bond that's this way? So option 1, option 2. You can speak. Option 1, why?
Because bromine's are better leaving.
Well, but bromine's leaving no matter what. And so this doesn't have to do with bromine. Like, she's going to leave whether we do this version or this version. And so we have to think about our good friend Zaitsev. So based on Zaitsev's rule, this one has 2 hydrogens and 2 substituted things. This one has 1 hydrogen and 3 substituted things. So number 2 is going to be more stable. So this is our Zaitsev. Cool. Now, second one. We're seeing that we're conking it. So immediately, what are we thinking? E1. That's what we're thinking. So let's think through it because, ooh, we have another girl here. So potentially we could do our GFP ranking on both of them. But conc, remember, it was primarily with secondary, tertiary alcohols. So let's see. Let's, for sake of argument, just start over here. So we would protonate this first, and then the leaving group would leave, and we would be left with this carbocation. And normally, we would say, okay, at this point, OSO3H minus is going to come and grab this hydrogen and fold in, E1 elimination, done. But there's an intruder inside the house. Which do you think is going to get you the carbocation faster? This thing that doesn't want to be a base and is a separate molecule, or this thing that's within the same molecule? So, what's going to happen is an intramolecular attack, where this lone pair oxygen is going to attack the carbocation. And when we do that, we are making a 1, 2, 3, 4, 5-membered ring. So, I'm going to make a 5-membered ring like a pentagon, where oxygen is one of them, and then I do my numbering. 1, 2, 3, 4, and the oxygen's 5. What else do I need to put on this ring to make it like the product of the previous step? Yeah, 2 methyls on carbon 1, and then I need an H on the oxygen. I really like this numbering strategy if you have to do an intramolecular and make a ring, because then you can just draw the ring like whatever the polygon is, like here, like pentagon, and then you can use the numbers to help match everything else. Okay, and then the last step, we're just going to make it neutral. So our product is going to be this SN1 intramolecular. So this is kind of the next level of, we have our expectations of, we see concentrated H2SO4, our gut is to go with E1, but then we're going to have to think through one or two more of these things. Just like E2 on the ring, we have to think through one or two more things. Last one I'll do very, very quickly. If we have an alkyl halide and we have magnesium, what are we forming? A Grignard. Okay, wait. That's lecture 3 stuff. This is completely different. So, here, if we form a Grignard, we know Grignards, if we were doing a water, Grignards are just kind of basic. So all this is going to do is, like, MGBR falls off, the OH minus is kicked off, and our product is just going to be cyclopentane, where we just, like, added an H. And so this is kind of a warning of, like, hey, all those other reactions we taught you are still fair game. They're still in play. And right now, lecture 6, you see alkyl halides and you're thinking substitution elimination. That's good. But don't forget about these other ones. So that's all I have for you. Thank you for coming to section. Hopefully this was helpful in kind of putting some of the pieces together. A lot of this just requires some practice for figuring out which one to use in the GFP system. I'll stick around if there are any questions, but have a good rest of your day. I'll see you all tomorrow in lecture.